Right, the next thing we're looking at is the next key concept, which is called mechanical energy. So when we talk about mechanical energy, what you need to understand about mechanical energy is that we're looking at something called motion energy, right? And when we talk of motion energy, it refers to two things. So far we've looked at gravitational potential energy and we've looked at kinetic energy. So gravitational potential energy works with position and kinetic energy works with motion. Now mechanical energy is both of them put together. So when a force acts upon an object, the object uses the transferred, that's important, energy as movement. And if an object is moving, it is using mechanical energy which has been transferred. So there's energy that's being transferred. So when I'm talking about mechanical energy, I can say that mechanical energy is the sum, that's important, of the gravitational potential energy which is your EP, and the kinetic energy which is your EK, which is your EK, of an object. So the object can be a person as well, in a closed system. Right, I'll just dissect that a little bit. So what we're looking at then, let's see, here's another color. When we talk about sum, it means addition, right, of the gravitational potential energy, which is your EP and your EK, of an object, right? So what we need to understand is if I'm looking at mechanical energy, I'm looking at one object. I'm not looking at multiple objects at a time. So if I'm looking at, let's say, this roller coaster that we can see here with these two kids in it, that whole thing is one object. We're only focusing on that object. So when we talk about mass, for example, and I'm going to show you now what we mean by that, we're talking about one sort of situation. So our one object when we're dealing with mechanical energy will be this cart with these two children in it, right? The next thing it says in a closed system. So what do we mean by closed system, right? If something is a closed system, you need to realize that the system is in isolation, right? If something is in isolation or in a closed system, that means we have no external forces, right? We don't take any external forces. So external forces can be something like air resistance, right? Or rather, I can even say a wind, right? Another type of external force is friction, because friction goes in the opposite direction of motion. So force of friction, right? Those are called external forces. So when we do this sort of situation, we do these types of calculations for mechanical energy, then we must understand that there are no external forces. We're only dealing with the information that we've been given. So what this means is a sum. It's the addition of the gravitational potential energy and the kinetic energy. So if I had to write a formula for that, I could say that mechanical energy is the sum of two things: the gravitational potential energy plus the kinetic energy. Right. And if I had to write that in a formula, The symbol we're going to use for mechanical energy is capital letter E subscript M is equal to the gravitational potential energy, which is your EP plus your EK. Right, this here is also measured in joules. This is measured in joules, and this is also measured in joules. And we use the capital letter J like we did before for each of these. Right? Now, I know that I can take this formula, and what I can do to it is I can expand it. Because let's say I don't have all the information. I know what EP stands for and I know what EK stands for. So what I can say is my mechanical energy is equal to mgh plus half mv squared. So all I'm doing is I'm expanding from here to here. Because the formula for EK is half mv squared and the formula for EP is mgh. So in terms of adding in my information, I can put my information into this kind of a formula. So the main formula where you get marks is either this formula or this formula here. In grade 10, we're quite lenient with you. So we're not too stressed about how perfectly you're getting this. But in grade 12, we're only going to give you the mark for EM is equal to EP plus EK. Right, so another thing we must realize here when we do this section is when we look at the mass here. Remember what I was saying before? When I'm looking at mass, the mass that I'm seeing here is of the same object. So remember the boy that was, remember I said I was standing in my classroom with the ball, right? And I was going to throw this ball or let the ball go. Right, so it's either going to fall or it's going to move up. The mass of this ball, right, must remain constant. So that value for mass for both EP and EK must be the same value. So it's either the same object, or we can even say the same group of objects. And all of these same objects or groups of objects are experiencing the same motion. They're doing the same thing at the same time. So if I look up here at this roller coaster, I've got these two kids coming down this roller coaster. Right, I'm just going to zoom into it. And they attach to the roller coaster. So when I'm discussing their mass, I can discuss it all together. So when I'm looking at the EP, it's all the mass is the same. If I'm looking at the EK, all the mass is the same. So that value must remain constant. And we'll get into it as we go into the section. So let's have a look at a little bit of an example of how we can use this formula, right? Just going to move up here. Oops, let's undo that. And let's just move the whole page and way over here. Right, let's have a look here. It says, calculate the total mechanical energy. So they want total mechanical energy for a ball which has a mass of 0.515 kilograms. It has a kinetic energy of 20 joules and is 2 meters above the ground. So we're going to write down some information. They want EM. Okay. They're telling you that you have a mass of 0.15 kilograms. They say that you have an EK that's equal to 20 joules. And then they're saying that you have a height which is equal to 2 meters. We also know that we could be using G, so we write it down as 9.8 meters per second squared. So now I'm going to say EM, my formula, is equal to EP plus EK, right? Which is equal to EM, which is mgh plus half mv squared. Right, so here's some bits of information. We don't know the velocity, but do we even need the velocity? Because look here, they gave you that EK value. They gave it to you at 20 joules. So what we're going to say is EM is equal to the mass, 0.15, times the gravitational acceleration. So times, I'm just going to move this here, 9.8, times the height, which is 2 meters, plus they already gave us this as 20 joules. So we're going to put that in. They gave us the EK. So I'm going to say EM is equal to, and I'm going to pop this first bit into my calculator, and I'm going to get 2.94 plus 20. So my total mechanical energy is 22.94 joules. And mechanical energy, we must know, is a scalar quantity, which means it only needs magnitude. So can you see there, you've got to read the formula carefully, you've got to read the question carefully so that you can make the right decisions. Because in this equation, they didn't give you velocity, but you didn't need the velocity here. You needed EK, which they gave you. In the question, they said the kinetic energy is 20 joules. So that's how you work a calculation like this. Please make sure you write down the formula, you expand, you substitute, you do the addition, you answer the final question. All right, let's have a look at another example. Oh, don't forget that this is example 6. We're going to do now example 7. Okay, so we look here. Right, example 7. Calculate the mechanical energy of the object that has a mass of 10 kilograms and a velocity of 3 meters per second and a height above the ground is 10 meters. So let's get all that information written down. So they want, choose another color, they want EM, which we don't have. They've given us a mass which is equal to 10 kilograms. They've given you a velocity that's equal to 3 meters per second. And they're telling you that the height is 10 meters. And I know when I do these calculations, I'm going to need G, which is 9.8 meters per second squared. So in all of this, we want EM. So we have a formula. The formula is EM is equal to EP plus EK. So the EP at this point, remember we must expand. We must say EM is equal to mgh plus half mv squared. Now what you would have noticed, it says an object has a mass of 10 kilograms. So we can see here that when we're dealing with these calculations, your mass for both sides of your, both EP and EK is going to be 10. So I'm going to say, I just want to reduce this a bit so I can work. I've got EM is equal to 10 times 9.8 times the height, which is also 10, plus half times 10, which is the mass, times v squared, which is 3 squared. Don't forget to sort that information out. So the first part is 980 plus half times 10 times 3 squared, which is 45. Add them together and EM is equal to 1025 joules in total. So that's how you would do something like that. Right, this example was a little bit different because instead of giving us EP or EK, they didn't give us anything. They gave us this information and they asked for total mechanical energy. Let's have a look at example 8. Alright, so if you look at example 8 says calculate the kinetic energy, the potential energy, and the mechanical energy. So we want kinetic, we want potential, we want mechanical. Of the object that has a mass of 1 kilogram, a velocity of 2 meters per second, and height above the ground is 50 meters. So we want mechanical energy, we don't know. We want the EK, which we don't know, and we want the EP. Now I know that the mechanical energy formula has it has everything in it, but they're not asking for the information like that. So what we have to do is we have to do 3 separate calculations. So we know that the mass is 1 kilogram. I know that the velocity is 2 meters per second. And I know that the height here is 50 meters. And I also know that when I do these calculations, I need that gravitational acceleration at 9 meters per second squared. All right, so let's start with each situation. Let's do EK. EK is equal to half mv squared. So a half times the mass times the velocity, which is 2 squared. And that's going to give me, 2 joules. All right. Then I'm going to do EP, which is equal to mgh, which is going to be 1 times 9.8 times 50. And then that's going to give me a total of 490 joules. All right. Let me see that. Now they want EM. So we're going to just go and we're going to say that EM is equal to EP plus EK. Now, in this question, when I'm doing this, I don't need to expand because I know that here's the EK here and here's the EP here. So I've just got to substitute it into my formula. So I'm going to go EM is equal to EP, which is 490, plus EK, which is 2. And that means that the EM is actually equal to 492 joules in total. So can you see, like in this question, there was no reason for me to write down this first formula then expand. Even if they gave me all of that information, they were asking for other things before that. They were asking for the things that make up my mechanical energy formula. So when you do these types of questions, read the question, write down your information, analyze the situation before you start. I'm going to do one more example and then I'm going to move on to the next thing. All right, if I look at example 9, it says a man is sitting on a 20-meter high building and has a mass of 50 kilograms. Calculate the mechanical energy. All right, so I know that I have a height here of 20 meters and I've got a mass here of 50 kilograms. I also know that I need a G value of 9.8 meters per second and a velocity value. And they want mechanical energy, so EM, which I also don't know. Right, what I need to understand when I have an example like this, it's also, you can still work out the mechanical energy, but I hope that you can notice now that this person is just sitting. So what I know about its motion is that the velocity of this person's motion is 0 meters per second. And if the velocity is 0 meters per second, remember what we said, there can be no kinetic energy. So what you're going to do is, what you'll realize here is that EK has to be equal to 0 joules because the velocity is at 0 meters per second. So, but I can still work out mechanical energy. I can say EM is equal to EP plus EK, right? And I'll say EM, and I'm going to expand, is equal to mgh plus half mv squared. And EM is equal to the mass, which is 50, multiplied by 9.8, multiplied by 20, plus half times 50 times 0 squared. See, that's where they give you your mark. So when you're looking at something like this, please make sure you don't fall into the trap of not doing the calculation and say that it's impossible, because 0 is a number. So then I can say that EM is actually equal to 9,800 plus 0. Because half times 50 is 25, but 25 times 0 squared is 0. So my mechanical energy is then 9,800 joules in total there. So even if they give you calculations where you're missing information, you need to make sure you put that information in. It's not in the question, but it needs to be here. So can you see here, out of habit, you would have noticed a couple of things about me. when I do these calculations, I make sure that look at my G and my V. I've put an arrow on top because out of habit, I know those are vectors. Also notice I've written down all my information. And then I analyze the situation and I realize because he was sitting, he's actually not moving anywhere. So he wouldn't have any kinetic energy. This part's important. Making sure you substitute that zero in shows your marker that you understand that there's no velocity, but you can still find mechanical energy. Alright, so when we do these types of equations, or why is this so important? Why is total mechanical energy so important? Is because what we've looked at before, and we did this in chemical change and physical change and chemistry, we're going to look at what does it mean to have energy? What's happening in a system that this type of energy, potential energy or kinetic energy, is so important to us, and why is the mechanical energy so important? And we're going to tap into some of the stuff from grade 9. Alright, the next section we're looking at is conservation of mechanical energy. So what we do know is, in previous sections we learned that when we have energy, like matter, energy cannot be created nor destroyed. So what we're looking at in this section is we're looking at the conservation of energy. So we've got two laws here. The first law we know about is the conservation of energy. You should get that into your books. The law of conservation of energy states that energy cannot be created nor or destroyed, but is merely changed from one form to another. So when we talk about that, what we mean by that is, if I had to look at a wind turbine sort of situation, you should get this into your book so we can have a look at how this type of energy works. Alright, so let's say I have this sort of setup. There's a darker color. Right, over here, when we talk about the fuel, we're talking about coal. And coal's a very good fossil fuel that they use in these sort of situations. And coal has chemical potential energy. It possesses that energy. Chemical, because coal is made up of carbon. And carbon is made up of atoms. And all atoms are matter. And we know that carbon is a chemical that I can find on my periodic table. So what happens with this carbon is we put this carbon into a situation where it burns. So it goes through the process of combustion, where it burns. And when it burns, this fuel over here will release what we say thermal energy. Now another word for thermal, and we looked at it in earlier chapters, is heat. And inside this tank over here that I'm seeing, right, this little tank here, I've got water. Now I know that if I heat up water, the water will eventually reach boiling point. And when it reaches boiling point, then I'm going to end up with steam. Right. So this steam over here is at a high pressure. And what it does is it starts to turn the turbine. Right? And once this turbine starts to turn, in the steam turbine, I'm going to find myself with kinetic energy. Obviously, after you draw this, you need to add all this information in. And I'm getting the kinetic energy from the movement of the turbine. And you do this in grade 9. We look at this in grade 9. So you have all the steam, it's creating this movement and creating this energy flow. And what happens, it goes into a generator. And what do generators do? Generators create a current. And when they create a current, I'm going to find myself with electricity. And electricity is electrical energy, electrical energy. So I started here with chemical potential energy, then I went to thermal energy, then I went to, which is heat energy, then I went to kinetic energy, and now I've got electrical energy. And once I've got this electrical energy, it can send electrical energy to either the power station, or it can send it to a building or facility, and from there it's going to come to our homes. Now in our homes we use quite a bit of different types of energy. For example, let's say you switch on, let's say you have the TV on, you've got light plus sound energy. Let's say you've got the heater on, you've got heat or thermal energy, right? So what I'm trying to show you is that when we talk about the conservation of energy, we're talking about the fact that this energy gets transferred from one type of energy to another. So I'm going chemical, thermal, kinetic, electrical, light, sound, heat, thermal. Can you see it's going in a sort of cycle? So what happens with energy is you can't just get energy from nothing, right? So it can't just be created, and you can't just destroy it. So it can't get, so there must be no loss of energy. And where this comes from, or this idea comes from, if you remember the beginning, and we look at example 1. So let's just look at example 1. So do that. If I look at example 1, example 1, we had that boy. Do you remember? There's a boy over here, and he was standing and he had to jump down. But when he was standing here at the top, he had a potential energy which was equal to 735 joules. Then, and that was when this whole thing was at 2.5 meters. Let's just write that. That was at 2.5 meters. But then we did a calculation for over here when he was 1 meter off the ground. And what we noticed then, his EP was then 294 joules. And I said to you that you cannot lose, or you cannot just destroy energy. So we wanted to know, how did he go from there to there if there's no such thing as loss of energy? So what I want you to think of, when he did do this jump, and he jumped here, right? I'm just doing that in pink, and he made the jump. As he was jumping, he was moving. And when you're moving, you don't have potential energy only. Sometimes you have kinetic energy. So what happened was, from that, in that period, from 2.5 meters, right, which was there at the top, to about 1 meter here, there was a conversion of energy between that period. It went from EP to EK. There was an energy that was transferred. So the gravitational potential energy became kinetic energy. There was a transfer. And when there's a transfer, that energy, so from 735 and 294, there was 441 joules of energy that was converted into kinetic energy in that little space, because as he jumped, he was in motion. So understand now that that energy didn't just go somewhere. It's still here, right? It's just that now it's not potential energy, it's now kinetic energy. So what that brings us to is the law for conservation of mechanical energy. And the law of conservation of mechanical energy states that, let's have a look here. I'm just going to move the screen up and bring it down. All right, the law of conservation of mechanical energy states that the total amount the total amount of mechanical energy in a closed system in the absence of dissipative forces, friction and air resistance, remains constant. So let's just break that down for you a little bit. Right. The law of conservation says the total amount of mechanical energy, which is your EM, in a closed system. Remember what we said? Closed means isolated, right? In the absence of dissipative forces, that's a correct terminology. Dissipative forces just mean external forces, right? We spoke about that, like friction and air resistance remains constant. That means it must remain the same. All right, so how would I write that in a formula? So what I could say is that if I have the mechanical energy, so I can have, if I have the mechanical energy at a point, it can either be at the top of something, or it can be before, or whatever the case is, right? Must be equal to the mechanical energy at any other point. So the mechanical energy at a point in a system, that can be at the top or before, must be equal to the mechanical energy at any other point in the system. That means it could be at the top, it could be at the bottom, it can be halfway, it can be at the afterwards, right? That's not too specific. So mechanical energy at one point must be equal to mechanical energy at another point. So what I can say is that in a formula, my formula for conservation, so my formula for this type of thing is the mechanical energy 1 must be equal to mechanical energy 2. Right, if I have to expand that out, I have formulas for mechanical energy. I know that for mechanical energy, it's EP1, can you see that? Plus EK1 is equal to EP2 plus EK2. Right, because the formula for mechanical energy is EP plus EK. And then I can further, right, 1 and 2 just means, let's say on this side 1 could mean the top of the building and 2 would mean the bottom. 1 could mean before and 2 could mean in the middle. Right, so 2 points, point 1 and point 2. Alright, so if I expand this, I've got MGH1 plus half MV squared 1 is equal to MGH2 plus half MV squared 2. Right, so the little 2's and the little 1's, they're just there to show you 2 points. This side of the equation is, let's say, point 1 in the system, and this side of the equation is point 2 in the system. So in the system. And that gives us our formula for the conservation of mechanical energy. This is the formula here. Then we expand there, and then we can expand further. So if they give you information here, you can stop expanding there. If they give you further information, you'll have to continue expanding. So we're going to have a look at what this means, right? I want you to also realize that I could have it as EM before is equal to EM after. Does it make sense? So then it will read EP before plus EK before is equal to EP after plus EK after. Does that make sense? Right, so this little subscripts that we're seeing here, they'll change, obviously, depending on what you're actually looking for. Right, so please make sure you get these formulas down, you highlight them, get these notes into your books, and then we're going to look at a little bit of a diagram, and we're going to analyze the situation. Right, let's have a look. Right, this example I'm showing you is an event that takes place in the Olympics. I'm just going to use a better blue. Right, it's called the ski jump. Right, so what you've got to do is you're going to start here from something we call the in run, right at the top, and you're going to get to the out run. So you're going to go down a slope, you're going to get to a peak point, you're going to jump off, and then you have to land on your skis. So let's have a look at what we mean in terms of kinetic energy and potential energy at each of these points. So in terms of some of our values, let's say the mass of our person, they're about 45 kilograms, right? We know we're going to need a G value, which is 9.8 meters per second squared. Right, that's some of our information. The other information we must draw from the actual table. So let's have a look here. For the first thing, for the kinetic energy, we know at the top of the slope, at the in run, the velocity is equal to 0. So if the velocity is equal to 0, then I definitely know that my kinetic energy is equal to 0 joules. So I don't have to do a calculation, it's fine, just like that, 0 joules. My potential energy in this situation is a bit different because it's mgh, which is going to be, so I'm just going to do this here. I'm going to say that EP is equal to mgh and EK is equal to half mv squared. So I'm not going to write the formula down. Here we have the mass, which is 45, multiplied by 9.8, multiplied by 100. Right, so let's get that value. Please work with me. Make sure you've drawn this diagram before you start with the calculations and give yourself enough space. We need a good 10 lines to draw this diagram. Alright, so you should be getting, for this one, 44,100 joules. Right, the next little step, I'll do this in another color. Let's do it in a bit of a reddish, right? The next one, I've got a kinetic energy here, although this time they've given me a velocity. So it's half times the mass, which is 45, times the velocity, which they're giving at 26 meters per second, squared. So now my EK at the second point here is 15,210 joules. Right? At this point, now we need to work out, oops, undo that. At this point here, it's 60 meters. So can you see this line that's lining up there? For the potential energy, I've got to take the mass, which is 45 times 9.8, multiplied by the height, and the height this time is 60. So now my potential energy is 26,460 joules. Right, so we can see that. Have a look here. It started here at 44, but the lesser the height gets, because this is happening at 100 meters, and then this is happening at 60 meters. So can you see that the closer you get to the ground, the less potential energy you have, because there's a lesser chance of you falling to the surface of the earth. Then we get to this point here, the third point in this little system. And at this third point, we've got a velocity of 20 meters per second. So you're going to get to a little bit of a dip. So I'm going to go half times 45 times, this time it's 20 meters per second squared. So now I've got 9,000 joules, right? But my potential energy is a little bit different, because now it's 30 meters off the ground. So it should be 13,230 joules, right? Are we seeing that sort of situation? So can you see I'm getting closer to the ground? It went from 44 to 26,000, now to 13,000. Then you're going to jump. When you're jumping, you're back at 26 meters per second at 60. So you're back now again with this other calculation. Your kinetic energy is now 15,210 joules. And your potential energy is 26,460 joules. Can you see at these 2 points? I'm going to label them point A here and point B. Can you see that they're equal to each other? Because we're saying that mechanical energy, because we have no external forces, the mechanical energy, can you see, is being conserved. Then we get here to the outrun at the end. When we get to the outrun, we have a different sort of situation now. So with the velocity, I made a mistake, sorry, it's not 0, it's 44.272 meters per second. So what I've got to do now is I've got to work out the kinetic energy. So the kinetic energy will be 0.5 multiplied by 45 times 44.272 squared. And that's going to give me 44,100.22 joules. My potential energy, because now at this point, my height is equal to 0. Which means if I do MGH, I'm going to have 45 times 9.8 times 0, which means I'm going to have 0 joules. So have a look here. The kinetic energy at the top is equal to the potential energy at the bottom. The potential energy at the top is equal to the kinetic energy at the top. So I can say I have conservation. So let's have a look at this sort of situation. I'm going to work out the mechanical energy at every point. Right, so let's do that. Right, for the in run, please make sure you're doing this in your books. I've got 44,100. So remember, I'm doing my total mechanical energy is equal to EP plus EK. I've got 44,100 plus 0, which is going to give me 44,100 joules. Right, at point A over there, I've got 15,210 plus 26,460. 26,460. And if I add all of that up, I'm going to get 41,670 joules. Right, at point here at the bottom, I'm going to call this point X. At point X here at the bottom, I've got 9,000 plus 13,230 joules. 230. And here I've got 22,230 joules. Right, at point B, I have 15,210 plus 26,460. Oops. 460. And then I'm going to get 41,670 joules. And then here at the outrun, I'm going to have 44 100 plus 0 is going to give me 44 100 joules. So can you see here to here? I've got conservation of mechanical energy. Alright, so when we talk about conservation of mechanical energy, these are the sort of setups that we're looking at. I'm going to show you another one and then we'll be done. Then you can go into worksheet 1 and worksheet 2. So we're just going to stop here for a bit and get into another example. Alright, if you're looking at this example over here, it says the diagram shows a roller coaster that starts from rest at position A at the top of a 40-meter high hill. It moves to position B at the bottom of the hill without friction and under the action of gravity. So it's just a natural motion. Initially, the roller coaster has potential energy and no kinetic energy. As it rolls down the hill under the influence of gravity, it loses potential energy and gains kinetic energy. At all times, the sum of the two energies remains constant. At the bottom of the hill, the roller coaster has its maximum kinetic energy and no potential energy. Right, question number 1. So let's have a look here first at what information we do have. So if we're working here. Right, it starts from rest over here at position A and at the top of a 40-meter high hill. Right, then it moves to position B at the bottom of the hill. Right, initially, that means at the beginning, right, it has potential energy but no kinetic energy. But we also know that that comes from that information that they've given us there above. It rolls down the hill under the influence of gravity. So we know that in these types of calculations, I must be dealing with gravitational acceleration. It loses potential energy and gains kinetic energy. It then says at the bottom of the hill, the roller coaster has its maximum kinetic energy but no potential energy. Alright, so what they want here in the first question says calculate the speed of the roller coaster at the bottom of the hill. So when you have a question like this, you have two things. At position A, we're at the top of the hill. And at position B, we're at the bottom of the hill. So now we must establish if we're going to use the letter A as our subscript, or I'm going to use the word top, or I'm going to use the word before, or if I'm going to use the word bottom or after. So the best thing for me here, the shortest subscript to use should be A and B. A refers to anything that's happening at the top. B is anything that happens at the bottom. Alright, so I know we must apply that the kinetic energy, so EP plus EK must be constant, because they're telling you here the sum of the two energies remain constant. That means the mechanical energy is constant in this type of an example. Right, the potential energy of the roller coaster due to its position in the gravitational field of the earth. So what's going to happen here is we need to understand that the formula we're using is EM of A must be equal to EM of B. So that's our first equation that needs to be written down. So once that happens, I can expand this formula into EP of A plus EK of A must be equal to EP of B plus EK of B. I know I can further expand this type of equation. The first one's going to be, so what information do I know before I start expanding things? what information do I know? So they're telling me that the roller coaster starts at rest, and it's at the top of so it starts at rest. So the V of A is equal to 0 meters per second. And they're telling me the H of A is equal to 40 meters. Right. They're also telling me that initially at the top, it has potential energy but no kinetic energy. So I know that the EP of A must be greater than 0, but the EK of A must be equal to 0. So already this information here, I know must be equal to 0 joules. So I don't need to actually do any calculations there. Then afterwards, it loses its potential energy and gains kinetic energy, right, at the bottom of the hill. So at the bottom of the hill, our information is what we're looking at. It says at the bottom of the hill, it has a maximum kinetic energy, but no potential energy. So the EP at B must be equal to 0 joules, but the EK at B must be greater than 0. So I know that information. So I'm going to fill this into my formula now. Right. So I've got EP is mgHA plus 0, I know that, is equal to 0, which I'm getting from here, plus half mv squared. Alright, so what they actually want here from our question, if we go back here, just going to zoom in here. It says, calculate the speed of the roller coaster at the bottom of the hill. So they want, they want this information. They want VB. So we're going to solve for VB. Right, if I'm looking at this type of question, let's see what I have. Right, I have this height of 40 meters. In terms of mass, I don't have any mass. So let's just look at what we do have, right? I know also that my G value is equal to 9.8. Maybe I should write that somewhere else. My G value is equal to 9.8 meters per second squared. Alright, so I'm going to say M times 9.8 meters per second squared. 9.8 multiplied by 40 plus 0 is equal to 0 plus half times the mass times VB squared. Alright, now if I'm looking at something like this or this sort of situation, if I look on both sides of the equation, over here and over here, both sides of the equation, if I take this M over to the other side, so I have an M here and I have an M here. If I take this M over here, it's going to become minus M. So M minus M gives me nothing. So in equations, when I see the same variable, M and M, on both sides of the equation, and they're both either positive or they're both negative, they can cancel each other out. So what I'm going to do is I need to get rid of that M. So I'm going to divide both sides. So at this point, I'm going to divide both sides by M, because they're on different sides of the equation. So we can write this down. They're on different sides of the equation, but they have the same sign. And if that happens, we can cancel them out, because they'll cancel each other out. So I'm going to say M 9.8 times 40 is equal to half mv squared b. And I'm going to divide both sides by m. And that's going to cancel. That's going to cancel. Now I'm left with 9.8 times 40 is equal to half mv squared b. Right. Now in all of this situation, I need to get VB by itself. Sorry. Oops. V squared B. I need to get VB by itself. So what I'm going to do to both sides is I'm going to need to get rid of this half. Alright, so I'm going to divide both sides by half. Alright. Oh, it keeps doing that. That's going to cancel each other. And now I've got, pop this into my calculator, 9.8 times 40 divided by half. And I've got 784 is equal to VB squared. But I don't want VB squared. I want VB. So I'm going to square root both sides. This square root is going to cancel out that sign. So I'm left with VB is equal to 784 square rooted is equal to 28 meters per second in the direction of motion. And that's how I would get that type of an answer. Alright, so this little bit over here is just a bit of extra information of how we get rid of the mass because we weren't given the mass. Now let's have a look at the second question. Right, it then says calculate the height. Calculate the height at which the roller coaster has half the speed you found in question 1. Right, so now in this situation, we understand that at the bottom of the hill, so let's just go back to this first question. Make sure you write here that, at the bottom of the hill. Don't forget to add this to your answer for question 1. Right, question 2, they want the height. Right, so they're looking for height, which they don't know. And they want us to use VB, which was 28 meters per second. They want us to use it as half the speed. So half of 28 is 14 meters per second. All right, so they want us to redo the calculation, except this time they want us to solve for the height, right? But they want us to use the speed over here. All right, so let's write our equation out. So I'm going to write there that EM of A is equal to EM of B. And I'm just going to start with my main equation. I'm going to say MGHA plus half MV squared A is equal to MGHB plus half MV squared B. Right. Here we're looking for height of B because we know height of A. So the mass here, same thing, we don't know the mass. This is 9.8 times 40 plus it's half times the mass times 0 squared, because that was your V of A was equal to 0 meters per second. How do I know that? They tell me here that it was at rest. My M here, same thing, M. My G value is 9.8 meters. Oops, I don't need that. 9.8 meters per second. They want HB plus half times the mass times V squared is now 14 squared. And that's what that's looking like so far. So let's just simplify this a little bit. On this side, I'm going to say 392m plus 0 is equal to 9.8 m 9.8 hb plus 14 squared times half is going to give me a 98m. Alright, so what I'm looking at now is a situation where I've got these m's. So what I can do is I can cancel them out. So divide everything by m, so that goes away, that goes away, that goes away. So now I'm looking at 392 is equal to 9.8, 9.8 HB, which we're looking for, plus 98. So what's going to happen is I'm going to take the 98 to the other side. And I'm going to have 392 minus 98 is equal to 9.8 HB. 392 minus 98 is going to give me 294 is equal to 9.8 HB. Then essentially, I want to get HB by itself. So I'm going to divide both sides by 9.8. And then I'm going to have HB, which is equal to 30 meters. All right, so that means that the roller coaster has half its maximum speed, when it is 30 meters vertically above the lowest position. Alright, so that's how you would do this kind of a calculation. So make sure you write down your information. Make sure you write down your formula. You expand, you substitute. Make sure you read the question. Remember when we said about mass, and like I said, it's always going to be the same mass. So you can kind of cancel it out if it's the same object, and it's usually going to be the same object. So let's look at another example. And let's have a look at this one. It says ignore friction for this exercise. Number 1, it's a multiple choice question. We're just going to go through the multiple choice question, right? It says which statement expresses the law of conservation of energy? The total mechanical energy of a system neither increases nor decreases during any process. Energy cannot be created nor destroyed. So is that true? We know that that one's definitely true. The sum of the kinetic energy and the potential energy of the system must remain constant. So I know that EM, maybe I use a different color. I know that EM is equal to EP plus EK, and that must remain constant. So number 3, that one's great. If the kinetic energy of a system increases and the potential energy of the system decreases by an equal amount. So that means if I saw it in that previous example, that, or the previous one with the roller coaster, not the one, the first example I showed you with the ski jumper, we saw that the mechanical energy, if the kinetic energy increases, then the potential energy has to decrease. So I know that that one's true. In the first one, it says the total mechanical energy of a system neither increases nor decreases during any process. That's correct as well. I want you to please make sure that all 4 of these statements, you know them. Very, very, very important. All 4 of them. So for number 1, all 4 options are correct. And I need you to please, 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 please go and study. You must add this to your notes. All 4 statements are going to come up in your tests and exams. You need to be confident enough to be able to say that all of these things are true about the law of conservation of energy. So please make sure you go, write this down somewhere. You must make sure that you have all 4 of these. Right, number 2. It says an object starting from rest slides down a frictionless 38-degree incline. So if I had an incline here, this incline, let's say, was at 38 degrees. So it looks like that. And what's happening is it has a vertical height of 14. So from here to here, from the top to this bottom ground over here, it's 14.0 centimeters. Great. Calculate how fast the object is going when it reaches the bottom. So let's say I do have an object. Here's my object here. And my object must go from here. It starts from rest. So the V at the top is equal to 0 meters per second. Right. And it has to slide down that way. And when it does slide down that way, it's going to end up over here. Right? They want to know how fast the object is going when it reaches the bottom. So remember what I said, it's not the bottom when it stops. They want the V of the bottom, which I don't know. Right? So what they want now is V final. So we got to sort that out. Do we have the mass of this object? No mass. But remember, we're dealing with the same object. And if we're dealing with the same or one object, then at some point I would be able to cancel the mass. Right. Another thing that we need to talk about is this here. Your height is equal to 14 centimeters, but I can't use centimeters. So when I want to go from centimeters to meters, it's a good conversion. This is going to come up. I must divide by 100. Or to go from centimeters to meters, I can times it by 10 to the power of -2. So that's another conversion that you can add to your list of conversions. So now I would say 14 divided by 100, which is going to give me 0.14 meters. Or I could have said 14 times 10 to the power of -2 meters. So I can use any one of these, can use it like that. It's the exact same thing. This is in scientific notation here at the bottom. And this top one here is in decimal form. And this is in scientific notation. Right. Another thing I'm going to have to use is G, which is at 9.8 meters per second. Right. I know that the V at the top is equal to 0 meters per second. And I know the V at the bottom, that is what we are looking for. Alright, so let's put it into the equation. I know that mechanical energy at the top must be equal to mechanical energy at the bottom. Alright. Can I move this? Okay. So let's expand here quickly. I'm going to say mgh top plus half mv squared top is equal to mgh bottom plus half mv squared bottom. So that's my actual calculation. I'm just going to zoom in here, so we're going to lose a little bit of our information, but you would have obviously written down your information. Alright, the first thing I've got here is mass, so I'm going to go M. G is 9.8, and at the top the height is 0.14. Plus, I know that my velocity at the top is 0. So I'm not going to have any, what do we say? I'm not going to have any EK, so plus 0. Because, yeah, plus 0 is equal to mgh. So I know at the bottom, my height at the bottom, so my height at the top is equal to 0.14. Great, meters. But my height at the bottom is equal to 0 meters. So I'm not going to have any potential energy. So I'm going to say that 0 plus half mv squared bottom. Right. If I look at the m's on both sides, I can divide both sides by m. So now I'm left with 9.8 times 0.14, which is 1.372, which is equal to a half v squared at the bottom. Right. Need to get rid of that half, so divide it both sides by 0.5 or a half, divided by half, cancel that out, and now I'm left with v squared at the bottom is equal to 2.744. But I don't want v squared, I just want v at the bottom. So I'm going to get rid of it by square rooting both sides. And I've got, that's going to cancel the square root, so I've got v at the bottom is equal to the square root of 2.744, and that's going to give me 1.65650, etc. I must round off to 2 decimal places, so I've got v at the bottom is equal to 1.66 meters per second, right? In the, don't forget to put this into your formula. Oops. In the direction of motion at the bottom of the incline. And that's your final answer. Please make sure it's a vector, so you need to make sure that you are putting the direction down. So when you're looking at your final equation, this is what your final equation should look like. All right. And this is what your whole sum should look like for number 2. Draw a diagram, write down all of your information, get into good habits. Write down all of your information, draw a diagram, substitute formula, expand, substitute, solve. Don't forget squares need to be square rooted. Don't forget it must be 2 decimal places. I need a direction. I need to write a final statement. The speed of the object when it reaches the bottom of the incline is 1.66 meters per second. All right, I'm going to do one more example and then you'll do worksheet 1 and worksheet 2.